All right, we're back again, and unfortunately I bite something up. There were two Screencast-O-Matic screens open, and I thought one of them was the one we were recording from, the other was extraneous, so I canceled the one and it closed the other one too. So the first part will not be recorded, but I'll leave that out there from last spring, so you'll still have that. Now, if it winds up that it saved it and is storing it somewhere else, then I'll do them both, but it looked like I lost it. But I'll leave the one from last spring. So we'll start again here, and we are recording now, and we'll go from current slide, and I'll even turn on the projector. Okay. I'll wait for that to come up. And by the way, I should have said this earlier. It's so disjointed today, I forgot to say it. If any of you at any point say, hey, can we have a break now? Fine. We can do it. These are long classes. I don't want you uncomfortable. If you're uncomfortable, you're not paying attention to what we're going on in here. You're paying attention to, and that's not got you where your mind needs to be. So if you feel like you need a break, say, hey, can we have a quick break? The answer is always going to be, yeah, let's do a quick one. Or let me finish this slide and then we'll do one, okay, or something like that. All right, now, a couple things about this text, okay? Number one, remember, Cengage, that does give the good deal as far as pricing goes, but in general, I don't like Cengage. But I have never found an author that I like better than Ron Larson. And there's a few reasons for this. On the back of your book, y'all don't have your books, but you'll see here there's 3 features back here. And okay. One of these features is a free website. You don't need a code, you don't need anything else. Your grandmother can pull up this website if she wants to. Anyone can pull it up, okay? It's called larsoncalculus.com, okay? And periodically I'll say, and you can find this at larsoncalculus.com. An absolutely free website anyone can go to, okay? There's also from the, I say this incorrectly, let me just check. Okay. In my pre-calculus text that he also is the author of, every example has a checkpoint that you can go to larsonprecalculus.com and see the checkpoint worked out. This one doesn't have that. But periodically you'll hit an example that says, go here and see it worked out. So you'll find it there. Okay. Number 2, your homework exercises. All the odd number homework exercises, and that's what I'm always going to give you. Number 1, they have the answers in the back of the book. The odd numbers have the answers in the back. So when you're working the homework, work that. See if you don't get the answer in the back, see if you can figure out how to. If you can't, don't get frustrated and think, I've got to wait a whole weekend before I can ask this question. I'm liable to forget it. No. Go to calcchat.com, another absolutely free website. You can go to that website and see the worked out solutions and tutorial help for the odd number exercises. Okay? And then there's another feature called calcview.com. Okay? Now that only has selected problems worked out there, but they go into even more detail than they do in CalcChat. Those will be, you'll see these little QR codes, I think that's what you call these, right? In your text, and where you see that, you can click on that, and the examples that are numbered in red numbers, those are worked out at calcview.com. So he has more tutorial help than any other author I've ever run into. So that's one reason I use his text. He's a good author too, but most calculus texts are pretty similar. He has these features that others don't. So I just wanted to say that before we got started. So let's start. Chapter 1, limits and their properties. 1.1 is a preview. What? Yeah, that's it. I thought this was the P chapter. No, that was preliminary. Is a preview of calculus. Wait, let me go back. It's going the wrong way. Preview of calculus. And our objectives here are pretty simple. Hey. What's that? Okay. Did you just add the course?
No, sir. I already had it, but I was apparently wrong.
I'm trying to find your name. There it is. And what do you go by? Pernisha? Okay. All right. Jackson. Okay. Oops. Pernisha Jackson. Okay. Is it Cal 1 or Cal 2?
Sir?
Cal 1 or Cal 2?
Cal 1.
Cal 1. Okay, you must have just added, because I printed this morning. So you must have just added today? Ma'am? Finish? Okay, wait, I don't see this as, where do you see this one? No, I think you're in English, Math 98. Okay, and that's on the Birmingham campus, not the Western campus. Okay. Okay. That's what you're, this one. Okay, got it. All right, that's in room 254. This is 255. Okay.
Thank you.
Yeah, I'll show you where 254 is. Developmental English is a little bit different from calculus 1. Okay. Not much, but a little bit. Okay. So, first objective, understand what calculus is and how it compares to pre-calculus. Probably most of you have a pretty good idea here. Understand that the tangent line problem is basic to calculus. Okay, we'll talk about that. And then the area problem is also basic to calculus. We'll be getting to this a little bit later, but we'll introduce it now. Okay, so this first part is sort of blah, 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 not too much quantitative, mostly qualitative. So first, what is calculus? Anyone have an answer to that? Well, there was a guy named Isaac Newton, and he had, I don't know if you'd call him a buddy, a friend, a co-scientist or whatever, a guy named Johannes Kepler. Johannes Kepler had studied something that scientists had been studying for centuries, and that was motion of objects in space, specifically the planets. For a long time, everybody just thought the Earth was the center of the universe and everything moved around it. Okay? It looks like the sun comes up in the morning, moves around and sets in the evening. Comes up in the east, sets in the west. And the stars did the same thing. The planets, though, sort of wandered around a little bit. And that's actually where the name planets came from. It means wanderer. The moon did its own thing, okay, but it still went around the Earth. Okay? Actually, it was the only thing that went around the Earth. And astronomers, had come up with all these intricate ways to describe what was going on. The planets gave them fit so, because they didn't follow regular patterns. The moon's pattern was regular, but it's just different from the sun and the stars. So they had sun and stars down, they had moon down, but boy, those planets were a problem. And then along came a guy named Copernicus, and he proposed the sun is the center of our solar system, and all the planets move around the sun. The stars are just out there, okay? But also, the Earth spins, and that's what makes it look like everything else is going around us. So, Copernicus came up with the idea, but it was this guy Kepler, and boy, how he did this, I do not know. But he came up with the 3 laws of planetary motion, and these described using areas of sectors and all sorts of really complicated things. He described the motion of the planets around the sun in an incredibly accurate manner. empirically. He could describe it. He had no clue of why that worked. And if my memory's right, he went to this brilliant mathematician and scientist named Isaac Newton and said, can you help me figure out why they do this? I know they do it. They follow this pattern, but I don't know why. Well, Isaac Newton then started having to describe what's happening on an instantaneous. Before this, all you could do was average. Average speed, average acceleration, average anything. But he couldn't do anything instantaneous. He came up with this thing called calculus, which was able to measure things in infinitesimally small periods of time. Okay? And this is basically became calculus. Now, supposedly around the same time, a guy over in Germany was doing the same type thing with a different impetus. His name was Gottfried Leibniz. He got to be a huge debate on who came up with calculus first. It became pretty obvious Newton did it first, but the big debate was, did Leibniz steal his idea and publish it first? And they argued for the rest of their lives on who did it first, okay? Some sort of contest, but we won't get into that. Okay, so what is calculus? Calculus is the mathematics of change. When we talk about change, we don't mean average change, we mean instantaneous change. For instance, calculus is mathematics of velocities, I already mentioned that one, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, what are those? Curvatures, variety of other concepts that have enabled scientists, engineers, economists to model real-life situations. Okay? All sorts of fields, maybe even pharmacy. And actually, I think pharmacy is, I keep knocking on that because to me it just seems like a weed horse. But when I get thinking about it, drugs release their effectiveness into the bloodstream on a continuous basis, not you take a pill and automatically it gets there. It distributes following basically an area under a curve type thing. So actually it may have more validity. So if I'm picking on pharmacy, it's not that I'm really meaning to, but I just say, why do they need calculus? But I think maybe you do. If economists do, I can easily see pharmacists do too. Okay. Although pre-calculus mathematics deals with velocities, acceleration, tangent lines, slopes, and so on, there's a fundamental difference between pre-calculus and mathematics and calculus. Pre-calculus is more static. Calculus is dynamic. Instantaneous change. Pre-calculus gives you the average here, the average there, the average there. Calculus describes what's going on every instant in the motion. Okay? Here are some examples. An object traveling at a constant velocity can be analyzed with pre-calculus mathematics. If you're going at the same speed, you can calculate how far you've gone just using regular old arithmetic. But if you're analyzing the velocity of an accelerating object that's changing speed constantly, only way you can do that is with calculus. Okay? Slope of a line can be analyzed with pre-calculus mathematics, but to do the slope of a curve, which is changing constantly, yeah, you need calculus. Okay? So those are the examples of that. The curvature of a circle is constant. If you have a perfect circle here, its curvature is constant. Okay? You can analyze that with pre-calculus mathematics. But if you have a curve and you're trying to get analyze the curvature here as opposed to here as opposed to there, those are all different. This curve is down, this one's up. You need calculus for that. The area of a rectangle, we can do that. Regular math, okay? But to analyze the area under a curve rather than a rectangle, you need calculus, okay? Because a curve doesn't have length and width, okay? It's constantly changing, okay? Each of those situations involves the same general strategy, the reformulation of pre-calculus math through the use of limits, the limit process. I sort of hate to say this, but it's true. Of all the things in calculus, I really like limits the least, okay? But that's what's used to define everything else. But once you get it defined, you can go on and use the rules of calculus. The limit process, though, that slugs you through how to get there. Then once you get the rules in place, you do not have to worry about the limits anymore. But we will do the limit process. So one way to answer the question, what is calculus, is to say that calculus is a limit machine, okay, that involves three stages. First stage is pre-calculus mathematics, such as the slope of a line or the area of a rectangle, okay? Second stage of the limit process, and the third stage is the limit process, and the third stage is then the calculus formulation. So pre-calculus mathematics will give you a certain piece of it, and this, to me, this is really fuzzy here. It's not making a lot of sense. I know where it's heading, and that's why it makes sense to me, but I can imagine where you're sitting, you say, what are they talking about? But we'll get there, okay? We'll actually be using regular areas of rectangles here. Then we'll do a limit process, and that will lead to calculus. That's what they're talking about, okay? Here's some familiar pre-calculus concepts coupled with the calculus counterpart, okay? All right. These really have very little to do with each other, okay? They're just different examples, okay? Without calculus, you can, if this is a function, the graph of a function, and you know a value of your x here, at that value, plug that in here, plug c in for the x, and you get the y value for here. That's what you did in pre-calculus. Pre-calculus is calculus of functions. You figured out how to do this. It's pretty straightforward, okay? Now, that's all you can do, though. Given an x value, calculate the y, okay? That's it. However, with differential calculus, what if you had a function here that was undefined here? Now, I don't know if you remember, in pre-calculus algebra, you probably did some functions that were rational functions. Remember those? A ratio of a polynomial up here to a polynomial down here. And what did we do to solve those? Typically what we did was factor everything inside. Factor the numerator, factor the denominator. If there were any common factors between those two, when you factor them, then you could divide those out. Okay? But in the original problem, okay, where this factor down here was 0, that would wipe out your denominator completely. It would not be defined there. So when you drew the graph, you had to put a hole in the graph at that value that you divided out. Do y'all remember the holes in the graph? I don't know if you do or not. That's what you ran into. With calculus, you can deal with that. That would be very difficult to deal with here. Okay? You just find out there's a hole in the graph. But here you can do the limit and find out the limit as a function approaches c, where it's not defined, is that value, whether you approach it from the left or from the right, so you can assume and deal with it even though it's not defined there. You can't do that without calculus. Here we have the slope of a line. Now, if that's a straight line, yeah, you can calculate the slope, rise over run. But if you have a curve and you have a tangent line here, you can still do, with calculus, rise over run for that instant right there. It doesn't work there, or here, or there, or there, but it works right there. Here you can only do it if it's a straight line. Here you can find out at every point on the curve what the slope is. Okay? Only with calculus, not with pre-calculus. Now this is similar to that one, only a little bit different. If you had a curve here, this may be representing your trip here this morning. I left Southside Birmingham and drove, had to get through UAB and all that kind of stuff. My function junction is still torn apart, so I had to go across all that, and it was a pain in the neck. It was a wreck on the way. It was awful. So anyway, finally got on the interstate and came. So when I hit the wreck, I had to go backwards, away from where I was going to go, make a detour, and then come back. And then when I got on the interstate, boy, my slope went up. So this doesn't fit exactly. Okay, I should be down here. Okay, this is okay. But between any 2 points on my trip, you can measure how far I had driven and how time it took me to get there. That would be my average speed. Okay, that's what we're talking about down here too. That would be the slope of the secant line. But at any moment in my trip, what my speedometer was reading was my speed, not here or here or here. At any point, that's your slope of the tangent line. And that's what calculus can do. This can only give you average speed between 2 points. This can give you instantaneous speed at any 1 point. And that's the same thing here. If you're going along, t is equal to 0, t equal a, you're at this speed, t equal b, you're here. It looks like here you're moving, here you're, I can't tell. Okay. But if you're changing speed, no, I'm sorry. You can do the average speed between these 2 points, measure the distance and between those 2 times, then you have your average speed. Here you can determine the instantaneous rate of speed at any time t equals 0. Again, this is blah, blah, blah. Qualitative, not very much quantitative here at all. Here's the one we were talking about before, the curvature of a circle. That's constant. It's fixed for a circle. But for a curve, down here, the circle would be here. Here, the circle should be a lot bigger than that. Here, the circle would be down here. So your curvature of a curve is constantly changing. Sometimes positive, sometimes negative. Okay, constantly changing. The height of a curve at x equals c, this is one we did earlier. Here is the maximum of the height. You can't get this. You can just keep measuring, and then go down and say, well, somewhere in there. Well, this tells you exactly where you reach that maximum with calculus. Here's a tangent plane to a sphere. That works okay. But a tangent plane to a surface, which is constantly changing, that needs calculus. Direction of motion of moving along a line, that's easy to give. But direction of motion on a curve that's constantly changing, that needs calculus. Pre-calculus, calculus. Again, blah, blah, blah. Oh boy, here we go again. Without calculus, you can determine the area of a rectangle. Length times width. Pretty easy to do. But what about the area under this curve? Well, that's not a rectangle. It looks more like a trapezoid, but it's not exactly that. If that's a curve, not a straight line there. But you can approximate it, but you can't get it exactly. Calculus can give it to you exactly. The work done by a constant force, if I'm pushing with a constant force on this table, I can figure the work that I do by the force times the displacement. That's from physics. However, if it's a variable force that's changing constantly, like a spring, then I need calculus to do that. Okay? The center of a rectangle, no problem there. Just do the diagonals where they cross, that's the center. The center of an area under a curve, that's called the centroid of a region, that needs calculus. There's no way you can do it any other way except calculus. We'll get there later. Okay. Length of a line segment, yeah, I can take a ruler and measure that. You know, the distance formula, the square root of the difference of x squared plus the difference of y squared. Yeah, that's doable. How are you going to do that here? The length along the curve, you'd have to have a flexible ruler and keep it right in place. That would be awfully hard to do. Calculus can give it to you exactly. Guess what? It uses the same principles as this, only, again, incrementally. Okay? And you sum them all together. Man, they got more of these. The surface area of the cylinder. I can do that because I can pretend that I cut this surface here, lay it flat, and then I have a rectangle. Yeah, I can do that. Okay? How about surface area of that? Duh, how do we do that? It's actually very similar to this, only you do it incrementally, and you can come up with it. The mass of a solid of constant density, yeah, area times density. Volume times density, not too bad. So the mass of a solid with variable density, in other words, it's denser on this end than it is on that end, yeah, you're going to have calculus for that. The volume of a rectangular solid, yeah, length times width times height. I can do that. But what of the region of a surface here that doesn't have fixed length, width, or height? Boy, you've got a problem there. Calculus can do it. The sum of a finite number of terms, yeah, you can always add those up, no matter how many you got, as long as it's finite. But if you have an infinite number, you're going to need calculus to do that. Okay? Now, we're not going to do all of this in this term. Okay? Some of this will be in Cal 2, some of it in Cal 3. Okay? But this is what calculus enables us to do that you couldn't do otherwise. Okay? A lot of blah, blah, blah. Okay? 3 pages of blah, blah, blah. Now let's look at, we're on page, if not many of you have your book, a few that do, page 49, the tangent line problem. And by the way, and for those who have your book, you notice the first of the little historical blurbs they have here. Here's a woman named Grace Chisholm Young. Okay? It's pretty sad parts of this, but it's really encouraging other parts. She was a brilliant mathematician, but back at a time when women were not supposed to be brilliant mathematicians. So she had to publish some of her early work under her husband's name so people would pay attention to it. And once he became very famous for his brilliance in mathematics, then they said, well, this is actually my wife, you know. And then they started paying attention to her. She would not have been able to publish without using either a pseudonym or somebody else's name. It's sad but true. So if something like this is of interest to you, that's a potential paper topic. Of course, this can't be your source. This would be the source of your idea. You have to go out to a library, someplace else, and find the reference material for that to use for the source of your paper. But we'll get there later. I just wanted to point that out. The book has these periodically. Okay. So here's a tangent line problem. Okay. The notion of a limit is fundamental to the study of calculus. So here's a brief description of 2 classic problems in calculus. First, the tangent line problem, and then we'll do the area problem to give you some idea of the way that limits are used. The tangent line problem we'll be using first in this. Area problem will be a later chapter. This will be, actually we'll be using it later in this chapter, and in the next chapter, in several chapters, this will be chapter 4, I think, before we actually hit that. Okay? But we'll introduce it now. Some idea, give you some of the way limits are used. All right. Here's a situation. We've seen several of these already. You're given a function, f. This is the graph of that function, f. Y is equal to f of x. You remember that from pre-calculus. And you know a single point on that line. It could be that point, this point, some point on the line. You're asked to find an equation of the tangent line to that point. Now, if this was a secant line between this point and that point, I can do that. Okay? I can do it without too much problem. Find out the x value here and the y value, the x value here and the y value, and then do the slope between these two, and then do the point slope formula. Whatever you want to do, you can do that. The problem with the tangent line, you only have one point. So you can't calculate the slope the way we did before. So you can't get any further than that. Okay? So this is the tangent line problem. How do you determine the equation for that tangent line? Okay? All you know is the function that that point is on, and you want to know the thing. Only one point. Really hard to do without 2 points. Okay. Except for cases involving a vertical tangent line, and actually a horizontal tangent line is really easy too. The problem of finding a tangent line at a point P is equivalent to finding the slope of a tangent line at point P. So yeah, those are basically the same thing. You can approximate the slope by using a line through a point of tangency. Okay? There's your point of tangency, P. And you want the slope of the tangent line. Well, let's first do the slope of some other point here. Like I said, if you have 2 points, it's fairly easy to come up with the slope. Okay? We're going to call this, the x value here is C. I wish I had drawn this better. This is C, and there's f of C, right? When I taught my pre-calculus algebra class, I would tell them the most important thing for you to remember in this class is y is equal to f of x. If you remember that, you got it not. So if this is your x at C, your f of C is going to be the y value. Okay? So you have one. Well, let's go over a little way. Now this looks like a pretty long way to me, but let's change the x a little bit. And that's what we call a delta x. Delta meaning difference. So this is a non-zero difference. So we're going to go from C to C plus delta x. Okay? So now this point is going to be C plus delta x here. That one right down there. Well, what is this value? It's f of C plus delta x. The y value is going to be f of whatever the x. So, and I guess this is the first time I've done this. Yeah, here we go. Notice I can, my computer, this tablet computer it's a tablet computer and it has an ionizing pen with it, so I can write on the screen. If it's projected, that's stored. I can wave my arms, it's not stored. So that's why I try to go back. So this value right here is x equals C. So this value right here, y is equal to f of C. Right? So the point here is C, f of C. X, y values, C, f of C. Right? So move the C over a delta x. So this value here on x is now C plus delta x. And this point up here will be on that curve. That's y is equal to f of x. Why didn't they say that somewhere here too? This curve right here is y is equal to f of x. Okay? So this value here, the y value here, is f of this x value, C plus delta x. Okay? So this is the x value here, the x value there, the y value here, the y value there. So this is the difference here is f of C plus delta x minus f of C. That's your rise, right? Rise over run. The run here is just C plus delta x minus C, which just becomes delta x. Oh, that was pretty easy. Okay? So therefore, this is a secant line between 2 points, and you can calculate the slope of that. The slope of that is y2 minus y1, which is f of C plus delta x minus f of C. That's your change of y from here to there. That's the change of y. F of C plus delta x minus f of C divided by C plus delta x minus C. That's just going to be delta x. Okay? So that is, now, flashback. I don't know where you did your pre-calculus, if you did pre-calculus, but in the text that I used, Larson text before this was pre-calculus, they called this a difference quotient. Y'all remember that? Difference quotient. This is the difference down here too. C plus delta x minus C. That just gives you delta x. So that's the difference. That's the difference, and it's the quotient of those two. Okay? And this difference quotient gives you the average slope between those 2 points. The slope of that secant line. Okay. Blah, blah, blah. Now, if P, which is your CF of C, is the point of tangency, and the Q, which is C plus delta C, comma, F of C plus delta X, C of C, Q, the X value is C plus delta X, And the y value is f of c plus delta x. That's that point Q. That's the second point on the graph. Then the slope of the secant line through those 2 points can be found. This is just what we did. I just did it on the slide before. The slope of that secant line is alpha c plus delta x minus alpha c divided by quotient here, c plus delta x minus c. Well, those c's go out. Then you got c alpha c plus delta x minus alpha c over delta x. Okay, that's the slope of your secant line. All right, now here is what we're going to do. We're going to let this Q, see, P stays fixed. That's where we really want the tangent line. Okay, so we're going to let the Q's get closer and closer to P on the curve. Okay, meaning your delta x is getting smaller and smaller and smaller. So this slope was here, this one is here, this one is there, that one's there, and as you kept getting closer and closer, the limit of the slope of these secant lines as your delta x gets closer and closer to 0 will be the tangent line. That's why we need the limit process, because you see the slope is getting closer and closer to the tangent line. It only reaches there in the limit when your delta x goes to 0. Oh, but wait. You can't have delta x equals 0, can you? You can't divide by 0. That was in pre-calculus mathematics. One thing that calculus does, it lets you take the limit as the delta x is getting close to 0. That's the limit process. Something you couldn't do in pre-calculus. You never can divide by 0. Okay? In calculus, you can take the limit as that denominator gets closer and closer to 0. And if that limit exists, then that's your slope of your tangent line. Okay? That's the limit process that bridges between pre-calculus, where you can't divide by 0, to calculus, where you let that limit go to 0 or approach 0. Okay. Now that was just blah, blah, blah. Okay? Now we're going blah, blah, blah the area problem. Okay? The second classic problem in calculus is finding the area of a plane region that is bounded by the graphs of functions. Yeah, we want to do that, don't we? Remember I said Newton was trying to help Kepler figure out why his laws work? Well, one of his laws was the area of the sector of a planet's motion around the sun for any time period is the same no matter for that given time. So when it's out here moving very slowly, that area is the same as here. When it's moving fast, the area is the same. That was Kepler's second law of planetary motion. He knew it worked, but he didn't know why. Well, Newton had to come up with a way to measure the area before he could describe why it worked. So he had to develop calculus. Okay, come up with a whole new math to explain a problem that a friend had, or somebody else had. Okay, and this is also solved with the limit process. In this case, the limit process is applied to an area of a rectangle, which we can do to find the area of a general region. Okay, and you'll find it's pretty close to being similar. As a simple example, consider the region bounded from x equal a to x equal b. And here is your function, y is equal to f(x). We're not looking for a tangent line now. We're looking for the area under this curve from x equal a to x equal b. Okay? How are we going to do that? Because it's constantly changing. You don't have any rectangle. Well, you could pretend you had a rectangle. Let's divide this into little delta x's, changes of x's. And if you did a little rectangle here, the area under that rectangle is very close to the area under the curve. Not exact, but close, right? The trouble is, this is changing here. So you either use the left-hand end, the right-hand end, or the center point end. It doesn't matter, just choose a point there. That's the height, there's the width, delta x, and that would be approximately the area. Okay? So and we're going to sum all of these up. We're going to do the next one, the next one, the next one, the next one. So these are getting bigger here, then smaller again, then bigger again. So do all these little skinny little rectangles and add them up. right? Well, guess what? That's going to be awfully close to the area under there. How do you get closer? Make the delta x smaller, skinnier. Now it's really close, okay? And you do that summation. Later we'll call that an integration. Summation becomes an integration. Again, as you're letting your delta x get closer and closer to 0. That limit process is going to give you the area under the curve. Now, I've just given it all away. Here's how they describe it. Yeah, this is what they say. Approximate the area with several rectangular regions. Here we start with 4, and this one's going to be here. We're going to use the left-hand end here. This is going to undershoot the area under the curve pretty significantly. This undershoots it here, but overshoots it a little bit there. So that's going to be pretty close. This one undershoots it completely, and that one undershoots it completely. Okay? But it's going to be fairly close. How do you get it a better x? Drop these in 2. Put another one in between each one of those. So now rather than having this big pink area here, you have 2 smaller pink areas. So you're closer here, you're even closer here and here, perhaps, and certainly here and there and there and there. So you've made the error less. We'll keep getting the delta x's smaller and smaller and smaller. As soon you are very close to the area under there. The limit as that delta x approaches 0, that will give you your area under the curve. That's what calculus does. Uses the limit process to give you an exact value of something you couldn't calculate before. As you increase the number of rectangles, the approximation tends to become better and better and better because the amount of area missed by the rectangles is decreasing ever so slightly. Your goal is to determine the limit of the sum of those areas of the rectangles as the number of rectangles increases without bound, meaning the delta x is going to 0. Whoa! There was section 1.1. Now, how in the world they came up with any homework exercises here? We didn't do a single thing numerically at all, okay? But they do give you some, and again, now these are not probably as crucial as some of the others, but once you do see your books, can use them. Okay. The odd number exercise up here at the top, it says see calcchat.com. Remember that was one of those things. calcchat.com for tutorial help and worked out solutions for the odd number exercises. So what I would do as a homework exercise for you, say do any of the odds 3 through 9. Okay, possibly 11. All those odds have the answers in the back, but they also have worked out tutorial help and worked out solutions at calcchat.com. But in addition to that, one of these, number 3, is in red. When you see your book, you'll see all these other numbers are black, 3 is red. Well, here's the QR code. All you have to do is get your cell phone or whatever device you're using, click on that, and you'll go straight to calcview.com. The symbol, the QR code, and the red exercise number indicates that the video solution can be seen at calcview.com. So there you can see it on your cell phone. Usually only one of those per section, but not every section will have them. This one just has that one, number 3. But that may help you see it, and then you can do better on the others. All right. You can do those odds if you want. We didn't do any samples of them, but I think you can probably figure them out. Okay. So let's move on to (1.2). Now, I get carried away here. 1 minute left? That's what I was just going to say. Let's stop there. We got one section covered, not very much to do on homework-wise, but you can look at that. Go back and look at the P chapter and see that we'll start with 1.2 next time, okay? And unfortunately, next time is next Wednesday, 1 week away, okay? So we'll catch you then. And hopefully by then, I can't promise it, but hopefully by then, I may have most of the stuff up on Blackboard and all that. Good deal. I'm sorry?
I said, if you ever need any kind of assistance with that, just bring about the office.
Oh, what office is it?
Jim.
Oh, Jim. Oh, you work with Jim.
Yeah, I work with him. I'm a part-time
I think
employee.
I've seen you over there or
Yeah,
something.
I'm
Yeah,
always
okay.
in the back.
Okay. Do you have any idea why it was doing that?
It may just need to be tuned up.
Okay.
Yeah, just bring it by whenever you're free.
Okay. All right. Thanks.
Sure.
Now, some of the guys laugh at this old computer over there.
I think that was my old computer.
Oh, okay. So you know why they're laughing at it then, don't you? Okay. I'm sorry.
For the research paper, does it have to be insight quotations or like any insight sources in the paper?
Only if it fits your paper. I mean, you can use either quotes or you can just cite where you got the information if you didn't do a direct quote. Yeah. Yeah. Does that make sense?
Yeah.
Okay.
For the class 113, math 113,
Uh-huh.
are you going to cancel that class?
I don't know now. I probably won't know until this afternoon. Can you do the one on the Birmingham campus, or do you know? You cannot. I think I talked with you on the phone, didn't I? Yeah. That's why I thought. I'm going to, how many finally showed up there today?
Only 6. And
Just
the
those
3 that were on it, 2 dropped it and only 1 is pre-registered. So it's 7 in total.
Okay. I don't know if they're going to let it go or not.
And that's the only Birmingham in here, that's the only 2 that's there.
There's the only 2. And that's the only way we're going to get it to keep is because we only have 2 sections, 1 on each campus. So I'll have to talk with my boss and see what they'll allow. I may have to talk with Miss Jabber. Miss Jabber too. They may prorate her salary because it has so few students, but she may still be willing to teach them. So it's a lot of ifs. I'll have to find. What's that?
When will you know about it?
I'll try to find out this afternoon, but see, I've got a class coming up right now, so I don't have any. I have 5 minutes between my first class and second class, so I'll be through this one at 2:25. Is that right? Yeah. So sometime after 2:30, I'll try to find out.
Thank you.
Okay. Sorry about that. What's that?
I think it was like 2:30.
I can't.
2:30.
2:25. I think is when it ends.
Yeah.
So I did something dumb right then. So actually, I needed to do it anyway. I didn't realize I needed to do it. I have 2 different flash drives. I only have 1 port, so I had to do that anyway. Oh boy, the more they come, the worse it. I mean, no, I didn't say that. Did I? Okay. All right. Hey, welcome back. Good to see you. How'd y'all wind up in the tournament? I know y'all went pretty far, didn't you?
Yeah, we got third.
Third. Fantastic. Yeah. My computer is not doing well today. Ah, there it is. Okay. Now it's doing better. Because I said that. Okay. Okay. Wait a minute.